Hello and welcome back. In today's video, we're going to be going over the 2025 AP Physics E E&M free response questions for Form J. Let's get started with question 1. So here we have two coaxial cylindrical shells and they're both conducting. And we know that the absolute value of the total charges on the shells are equal. The inside has a positive, the outside has a negative charge. So let's start with part A, section I. Using Gauss's law, derive an expression of the magnitude of the electric field as a function of the radial distance from the center of the capacitor. And R is going to be away from this inner cylinder, but it's going to be less than this outer cylinder. So let's start with an expression. What expression are we going to use? We're going to use Gauss's law over here. EdA equals Q enclosed over epsilon. But what's EdA? EdA is going to, so E is constant, but the area refers to the surface area of your Gaussian surface. And what's your Gaussian surface going to be? So let's draw that here. So it's actually going to be this. So we're going to draw it around here, where this represents R. So if you draw all the way to the center here, that is R. So that means that our Gaussian surface's surface area is going to be 2 pi times R, that's the circumference of a circle, times L to get the surface area of our cylinder, not including the ends, just the middle section. So we have 2 pi RL times E, that's our electric field, equals. Now what is our enclosed charge? Let's just zoom in here. Our enclosed charge, we're being given the surface charge densities, meaning that we have to multiply the surface charge density, so I'm just going to write O, but that represents this figure over here, O times 2 pi L, but then what's our radius now? Our radius is going to be fixed, no matter how far we go away until here, the radius of your cylinder is still going to be R1, so times R1 divided by E, and that E refers to epsilon over here. So we have 2 pi RL, R referring to how far your radius is going out, times your electric field equals your sigma value here times 2 pi L times R1, meaning this cylinder here which stays constant in size, divided by E. So all we have to do is solve for your electric field. So E equals, if we divide the 2 pi and L's, so divide the 2 pi, divide the L, we can get rid of this entire part over here. Meaning your electric field is just going to be your sigma value times R1 divided by R times epsilon, so R times epsilon. And that's your answer. We can even draw it out over here. So E equals your sigma 1. Remember, not 2, we're using 1 because we're looking at the inner cylinder, times R1 because that stays constant in size, divided by epsilon times R. And there we go, that's the function for the electric field. Now number 2, derive an expression for the absolute value of the potential difference between the outer and inner shells in terms of R1, R2, and sigma 1. Now notice, we're not being given the value of sigma 2, so we don't have to worry about this shell. So what equation can we use? If you go over to your formula sheet, you can see that the potential difference is going to be equal to the negative integral from A to B of your electric field dr. So we're asked for the absolute value, so it can just be positive. So let's write out our equation over here. So for part 2, delta V is equal to the integral of E dr. And we care about from, where is it? R1 to R2. R1, because we're looking at the outer and inner shells, just this difference over here. So R1 to R2. Well, how can we actually solve for this? We're going to write it over here in decimal so that it's easier to draw. So we're going to write V is equal to the integral from R1 to R2 of E dr. But what's our expression for the electric field? It's going to be mu times R1 over epsilon times R. But everything but the R down here is a constant. So let's actually bring that out. So we have mu times R1, and this is all divided by epsilon. And now we're just going to be integrating 1 over R. Well, what's the integral of 1 over R dr? The antiderivative is just going to be ln R. So we're just going to have ln, and we have to plug in our bound. So ln of R2 minus ln of R1. And if you remember your logarithm rules, this is just going to be equal to ln of R2 divided by ln of R1. And that's your answer. Your voltage difference is going to be equal to sigma O times R1 over E times the integral times ln of R2 divided by R1. Well, that's your answer for voltage. So let's just write that over here. Your voltage is going to be equal to sigma 1 times R1 divided by E times ln of R2 over R1. R2 divided by R1. And there we go. Now on to part 3, or III. On the axis shown, sketch a graph of the electric field as a function of R. Well, we're being told that these are conducting shells, not insulators. So what's the electric field inside of the shell? Well, actually, it's going to be 0 because all of the charges are going to be right at the very edge here. So there's nothing inside. So if the electric field all the way up until R1, it's just 0. There's nothing here. And similarly, if we look outside of here, so let's say we're at a point all the way over here, here, like here, we're being told that the absolute values of the total charges on the shells are actually equal. And if we look at Gauss's law again, we care about the enclosed charge for the electric field. Well, Q1 plus negative Q1 equals 0. So no matter how far out I go, there's just no electric field outside. So this is also 0. But what about from R1 to R2? If we look at our equation over here, we can see that there's a 1 over R relationship. So we could just start up here and draw a 1 over R graph. And if you're ever wondering what that looks like, you just have to plot 1 over X, and you can see that it will resemble something like this. Anyways, that's part 3 of the graph answered. Now part B. A material of a dielectric constant K is inserted into the isolated charge capacitor such that the material fills the region from R1 to R2 as shown. And we have to derive an expression for the capacitance of this capacitor. And we have to begin our derivation by writing a fundamental physics principle or equation. Well, our equation for a capacitor is going to be Q is equal to CV. That's a common equation we know. But this doesn't include a dielectric constant. What does include a dielectric constant is this equation over here. Let's zoom in for this. C equals your dielectric constant times epsilon times the area of your plate divided by D. But how are we going to use this? And the way we could use this is actually by looking at the relationship with K here. In our original problem, we're being told that it's an air-filled charged capacitor. The dielectric constant of air is 1, so K is equal to 1. But in this scenario, we're having a new value of K. But if every other thing is being kept the same, then that means if we divided C new divided by C old, since everything else is being kept the same, this ratio is just going to be equal to your value of K here, your dielectric constant. So then that also means that all we have to do is find the capacitance of this capacitor with no dielectric constant, and we just multiply it by K, your dielectric constant. So let's do that. We know that that Q is equal to CV. Great, but then that also means that we have our capacitance is equal to Q over V. Q over V. Well, how can we get Q? How can we get V? We know that our charge is going to be equal to your sigma value times, and let's see over here, it's 2 pi R1, correct. 2 pi R1, 2 pi times R1 times L, and that's the value of your charge. And now we have to divide it by voltage, so divided by your voltage. And luckily for us, we have an equation for voltage over here. It's going to be sigma 1 again, so O times R1, and this is all going to be divided by E, times ln of R2 over R1. So this times ln of R2 divided by R1 divided by E. So what can we simplify now? I see an R1 here, I see an R1 at the top, we can cancel this out. I see, do we have any L's? No, we don't have an L, so we're not canceling that out. I see a shared value for this, so we're going to cancel that out. And essentially, all we're left with is this. But actually, we have E on the bottom here because we're dividing. So we can bring that up to the top. So then there's your answer. So C is equal to 2 pi, so I'm going to write the pi symbol, 2 pi times L times E divided by the natural log of R2 divided by R1. So R2 slash R1. But we're missing something here. That's right, you have to multiply the dielectric constant over here. So let me try my best to draw that. And there we go. That's the answer for your derivation. You have L, you have R2, you have R1. You have your physical constants, and you have the dielectric constant here. Actually, this should be the, there we go, epsilon. And that's your answer for part B of question 1. Now we're going to be starting with question 2, version J. So we have a rotating circular conducting loop of area A and resistance R, and it has an angular speed omega and period t. And we have an equation for the value of the magnetic flux through the loop as a function of time, and its flux equals BA cosine omega t. And we have to draw a bar graph, so we have to draw some bars over here in order to represent the electromotive force, the induced EMF in the loop. But how are we going to do this? All we have is the flux. Luckily for us, we have an equation sheet, and this equation sheet tells us that your electromotive force is here. Electromotive force is equal to the derivative of flux with respect to time. Luckily, all we care about is the absolute value. So what's the derivative of flux with respect to time? It's going to be BA sine omega t. It's going to be negative. It's going to be negative here. And as per the chain rule, we have an omega on the outside. But we care about the absolute value, so we can just write this. This is going to be d flux with respect to time. So d flux with respect to time. Now, how are we going to use this? If we plugged in 3 over 4 times the period, but how are we going to plug this in easily? If you go over to your mechanics equation sheet, you can see that the period is 2 pi over omega. So if I had 3 over 4 period, I can change this into 6 pi over 4 omega. And if I plug this in here, the omegas cancel out. So all you have to really do here is just write sine of 6 pi over 4. So you write sine times 2 pi, so you're going to do sine of 2 pi times whatever number's in front of the period. Sine of 6 pi over 4 is the same as 3 pi over 2, and that's negative 1. Since we're taking the absolute value, we can consider it as 1. And that's going to be the maximum value of your EMF. So we know the absolute value is going to be 3 bars high. So let's look at 1/4 of the period, for example. So 1t, so t over 4, this is going to become 2 pi over 4 times omega, so we're going to be plugging in pi over 2. Sine of pi over 2 is 1, so we find that the maximum value of the EMF also occurs at pi over 2, or 1/4 times the period. So now what we can do is just draw in a little shape for our bar graph. So I'm just going to draw a rectangle here like this, and there we go. But what about time equals 0 and 1/2 the period? Well, at time equals 0, we're effectively doing sine of 0, and sadly, sine of 0 is still 0. So 0. And what about 1/2 the period? Well, that's just going to be plugging in pi, because we're doing 2 pi over 2, so that's just sine of pi. Sadly, that's 0 as well. So what your bar graph should be looking like is at time equals 0, it's 0. Then we're having maximum EMF, then it's 0, and then again maximum EMF. Now on to question B. Derive an expression for the maximum induced current in the loop in terms of A, R, B, omega, and physical constants. And we have to use a fundamental physics principle, or equation from the reference information. And we're going to be using Ohm's law for this. Let's move up back to E and M. And you're going to be using V equals IR over here. So, V equals IR. Do we have an equation for voltage? Yes. We just solved it up here. It's going to be omega BA times sine of omega t is equal to IR. We're trying to isolate our current, so we just divide by the resistance, and we get this. Your current is equal to omega BA times sine omega t over R. Well, it is negative, so we're going to write that. But we want the maximum current. And the maximum current is dependent on whatever sine of omega t is. And the maximum value of sine omega t is 1. Well, it can be negative 1, and we can cancel out the negative. So we remove this, and there we go. Your I max, I'm going to write I max. The maximum current you can have is omega BA divided by R. And that's your answer for question B. Now C. On the axes shown below, sketch a graph of the instantaneous power dissipated by the loop as a function of time. Well, let's go back to our equation sheet again. We can find that your power is equal to your current times your voltage. Well, what else do we know? So we know P equals IV. Well, voltage is equal to IR, so we have I squared R. And what we're going to do here is try to find out what the power is proportional to. So first of all, what is our current proportional to? We solved it up here. We said that our voltage was proportional to sine of t. If V equals IR and resistance is constant, that must mean that our current is also proportional to sine of t. So current is proportional to sine of t. Well, we have I squared here, so that means our power is proportional to sine squared of t. And resistance is constant, so we don't have to worry about that. So how are we going to draw this? Let's see what a sine squared graph looks like. Okay, that's great to know. But what are we going to be drawing over here? Well, we know that if our current is at a maximum, our power dissipated is also at a maximum. If we have no current, we have no power being dissipated. And if we look over here, we know that V equals IR, so if we have no voltage, we have no induced current. At time equals 0, we have no current, because we have no voltage. But at 1/4 t and 3/4 t, we can see we have a maximum voltage and therefore a maximum current. And therefore also we have a maximum power dissipated. So I'm just going to write 1/4t here. And I'm going to also write in 3/4 t. So I know that a maximum value of our graph here is going to appear at 1/4 t and 3/4 t. And it's going to be 0 at 1/2 t and t. So now let's draw our graph. We know that it starts at 0, and it reaches a peak up here, and then goes down. We know that it reaches a peak up here, and then goes down. And then it reaches another peak up here, and then goes down. Your graph should look something like this. If the graders know that it's something relating to a sine squared graph, then you're probably going to get all of the points for this question. And there we go. Now part D. Indicate whether the sketch you drew is consistent or not consistent with the bars, and we have to reference the functional dependence between power and voltage. Well, let's actually write that. So we know power equals IV. We know V equals IR. So that means that your current is equal to V over R. So V over R. So that means you're having V squared over R is your power. Resistance is current, so we know that power is proportional to voltage squared. Now, is this consistent or not with the bars we drew? At 1/2 the period, we say that there's no power dissipated. At 1/4, we say that there's a maximum. If we look at our bars here, at 1/4, we have a maximum voltage. At 0, we have no voltage. So I would say that our sketch actually is consistent with it. So we can actually say on the bar chart, we can see that the maximum values for the absolute value of the EMF exist at 1/4 t, so t over 4, and 3t over 4. We can also see that 0 EMF exists at t equals 0, 1, so t over 2, and t. Well, t doesn't exist in the bar chart, so we're going to ignore that. Our graph accurately reflects this, as peaks exist at t over 4 and 3t over 4, since power is proportional to the voltage squared. And you can say power dissipated, and there you go, that's your answer. You know that your power is proportional to the power dissipated is proportional to your voltage squared. And when you have a max voltage, you have the max power dissipated. No voltage, no power dissipated. And there you go. Now we're going to be doing question 3. And this is the experiment part of the FRQs. In experiment 1, students are asked to use a graph to determine the resistivity of a circuit element that's connected to a variable power supply. And it's a uniform resistivity and it's cylindrical, and you have access to a voltmeter, an ammeter, and a ruler. So first, describe a procedure for collecting data that would allow you to use a graph to determine resistivity, including any steps necessary to reduce experimental uncertainty. So, we're trying to find resistivity. How are we going to do this? If we look at our equation sheet, we can find, so resistivity is over here. Here we go. R equals PL over A. And A means the cross-sectional area, so R equals PL over A. So, how are we going to do this now? So we have to first find our resistance, because we have the length, we have the cross-sectional area, because remember, we have a ruler, but we don't have the resistance. That's the missing part of this. How can we find resistance? Luckily, as we just used in our last question, we know that V equals IR. And luckily for us, we have a voltmeter and an ammeter. Meaning, that if we graph our voltage against our current, we can find the slope for resistance. And if we found the slope for resistance, we can just solve this like a normal algebraic equation. So let's write down our steps. Number 1, connect the ammeter to measure the current across the the circuit element. Number 2, connect the voltmeter to measure the voltage across the two ends of the circuit element. Number 3, measure the measure the radius of the circuit element and its length. And now number 4, set a voltage for the variable power supply. And once we do this, let's move on to our next steps. Measure the current and voltage recorded by the ammeter and voltmeter respectively. And once we have this, all we're going to be doing is repeat steps 4 to 5 for varying voltages. Now that we have all of our steps, we can just extend it out like this and put it to the top here. We're going to be doing part B, to determine how the collected data could be graphed and how the graph would be analyzed to determine the resistivity. So let's write that over here, B. We can plot a graph of the recorded voltage against the recorded current for each trial. The slope of this graph, as per V equals IR, is going to be the resistance of this circuit element. It's just going to be the resistance measured. So once we have this resistance, we can then find the cross-sectional area of our circuit element using the measured radius. Then, using R equals PL or rho L over A, over A, we can then solve for rho, we can just say solve for the resistivity, since we have all of the missing components. And there we go, that's how you can analyze the graph. Because what we're going to be doing is we're collecting the data, we're going to be finding components. We're collecting the data, we're graphing V equals IR, and the slope is going to be R. Then we use that resistance to determine the resistivity. So that's A and B done. Let's do part C, I believe. Yes. In experiment 2, students are asked to use a graph to determine the resistivity of another cell. So this is resistivity 2. Solid cylindrical resistors may have the same material but different lengths. The cross-section. So it's a fixed cross-sectional area, and the students measure the resistance between each ends, and table 1 provides L and R for each resistor. Now we have to indicate two quantities, either measured or additionally calculated, that could be graphed to produce a straight line to find rho 2. Well, let's look at our equation again. R equals rho L over A. We're told that we have a fixed cross-sectional area, so we don't care about that. But then all we have is we have varying lengths, we have a varying resistance. Well, we're measuring the resistance. So that means we don't have to change any data. So that means on our vertical axis, we're going to be graphing the resistance, so R ohms. And on our horizontal axis, we're going to be graphing the length, so L in meters. And now I'm just going to show you how to label everything. I'm not actually going to draw the graph. So we're going to do L of M, and we're going to have rho, the resistance, so R ohms. You can practice drawing the graph on your own, as it's great practice, but all I'm going to be doing is doing the calculations at the end. So your best fit line should look something like this. It's going to be a straight line starting somewhere near the origin. And using your best fit line, calculate an experimental value. First, let's find the value of our slope. So what I'm going to be doing is I'm just going to be doing the start minus 0, 0, since it does intersect at or near the origin depending on how you draw your line. So your slope is equal to, let's find the values. Remember, your ohms are on your y-axis. So 4 minus 0 because we're doing the origin, divided by 0.05. 0.05 minus 0. And we can just use decimals here. 4 divided by 0.05 gives you 80. So your slope is equal to 80. Now how are we going to use this? Resistance equals rho L over A. We know L, we know R, that's what we're graphing. Meaning your slope is equal to P, your rho over A. So slope equals rho over A, it's equal to 80. What's the value of our cross-sectional area? 5 times 10 to the negative 6. So that means rho is equal to 80 times 5 times 10 to the negative 6. 80 times 5 is 400, that's going to make it 10 to the negative 4. So this is equal to 4 times 10 to the negative 4. So let's just check, let's just double check. So we have 80 times 5 times 10 to the negative 6. And there we go. If you do 4 times 10 to the negative 4, you get the same answer. But what are the units? The units are going to be ohm meters. It's going to be the symbol for ohms times meters, so ohm meters. And there you go. You just found the resistivity. And I believe that's question 3? Yes, it is. Now we're on to the final question, question 4. Long parallel wires S and T are distanced 2D apart. They carry equal currents, but the currents are in opposite directions. So what are we trying to do? F1 is the magnitude of the magnetic force experienced on sphere 1 due to the currents in S and T. Okay. And F2 is the magnitude of the magnetic force experienced on sphere 2. And we're trying to see if F2 is greater than, less than, or equal to F1. Well, let's think about this. Remember your right-hand rules. For sphere 1, if we use a right-hand rule, we can find a current that's coming out of the page. So we're going to draw a little dot. And if we look at it from wire T, we can find something going into the page. So X. For sphere 2, if we look at wire S, we see something going into the page. And if you use your right-hand rule again for wire T, again, it's going into the page. So remember, your magnetic field depends on the distance. So of course, wire S's magnetic field is stronger than T. But again, these are in opposing directions. Whereas for sphere 2, they're in the exact same direction. So sphere 2's path is going to be having a much stronger magnetic field along this path over here. Whereas in sphere 1, it's weaker. And if we look at our equation sheet, actually you don't need that. You just need to remember that F equals QVB. And actually I'll still go to the equation sheet to show you. It should be somewhere here. F equals Q times V times B. If you have this, the stronger your magnetic field, the stronger the force is going to be. So that's why I'm going to be saying that force 2 is actually stronger than force 1. So let's say this. For sphere 2, the wires, which are going in opposite directions, provide magnetic fields that are in the same direction along the path of sphere 2. For sphere 1, both wires provide magnetic fields in opposite directions. Therefore, the magnetic fields for sphere 2's path are added, while they are subtracted for sphere 1. Therefore, a stronger magnetic field exists along sphere 2's path, and as per F equals QVB, sphere 2 will have a stronger magnetic force applied. There we go, that's why sphere 2, or F of 2, is going to be greater. Next, derive an expression for the magnetic field B total of the magnetic field at the location of sphere 2 due to S and T in terms of dI and physical constants. Begin your derivation by writing a fundamental physics principle. Well, the fundamental physics rule I'm going to be using is Ampere's law. So that's going to be somewhere here. There we go. BDL equals U times I enclosed. So if we just draw, we can actually draw it over here. We look at our diagram and we draw a little radius where this point is. What we can now do is write this. So we have the integral of BDL. I'm going to write that here. The integral of B times DL equals the mu times your current enclosed. Your current enclosed is just going to be I. Your mu is constant. Well, what is dl? Well, that's simply going to be the circumference of the circle over here. And we're looking at a distance away, so that's going to be d. So that actually means that this is going to be equal to b times 2 pi d. And let's just divide it to the other side, giving you that the magnetic field at any point here, any point along the circle, is going to be equal to mu I divided by 2 pi d. So that's actually really helpful for us. So we're going to say magnetic field of, let's say, due to wire t. So bt equals mu I, and this is going to be I of t, so I'm just going to write I, divided by 2 pi d. That's going to be the same for wire s. So magnetic field due to s is equal to ui divided by 2 pi d as well. Now remember, these currents are going in opposite directions, meaning that the magnetic fields actually sum at this location. So that means that our magnetic field total is going to be bt plus bs is equal to, so since these are the same, you're just going to be multiplying by 2, giving you ui divided by pi d. So we're going to draw that out here. B total is equal to mu times your current divided by pi times d. And there you go. That's the expression for the magnetic field total. And if you want to write it separately, what you can write instead is B total is equal to each part added. You can factor out a mu divided by 2 pi d, so mu divided by 2 pi d, and you're going to be multiplying that by the initial current, so that's I of t plus Is. That's the current in wire t plus the current in wire s. And there we go. So next, problem C. Later, wire t carries current 3I in the plus x direction. So no longer are they opposing currents, they're in the same direction. 3I in the x direction. At the instance shown, sphere t is a distance d below wire s and is moving with speed v. F nu is the new magnitude of the magnetic force experienced on sphere 2 due to the currents. Indicate whether this new magnetic force is greater than, less than, or equal to force 2 by writing one of the following. Well, force 2 represents what the force experienced here was. And now here's an interesting thing to notice. Here you have a much greater current total, but they're in the same direction, meaning that if you checked your right-hand rule, the magnetic field here is going to be coming out of the page due to wire t, but it's going to be going into the page due to wire s. So here they're being subtracted, here they're being added. So what is the new force going to be? So let's actually reference our derivation up here. I'm going to bring this down here. So we can see that instead of adding the currents, because they used to be going in the opposite directions, we're now going to subtract them. So we're going to do 3t, so 3it minus is. But since I is referring to the same variable, we're just going to do 3I minus I. But what you can see is that this just becomes 2I. In the past example, we were doing I plus I, giving us 2I. But here, we're doing 3I minus I, giving us 2I as well. So in the end, our forces are actually still the same. So F nu is equal to F2. As per the derivation in part B, if the currents were going in opposite directions, then we would add the magnetic field for sphere 2 at that point. Therefore, we were adding B plus B to give 2B, for example. However, in this scenario, one of the magnetic fields is in the opposite direction due to a reversed current direction. So now we are subtracting the magnetic fields. Also, this current is now 3 times greater in magnitude. So we are doing 3b minus b, which still gives us 2b. Since the overall magnetic field at sphere 2 is of the same magnitude, in both scenario 1 and 2, we can say that the forces experienced will be the same in both scenarios. And there is your answer. So just to quickly summarize, in this scenario you're adding the magnetic fields, and that's I and I, so it's just going to be adding them. But here you're subtracting them, but because this is 3 times greater, you're basically doing 3 times I minus I instead of I plus I. But I plus I is equal to 2I, 3I minus I is also equal to 2I. So that's why your forces are the same. Thank you for watching. If you have any questions about any of the work I've shown or why an answer is what it is, let me know in the comment section down below. Otherwise, goodbye.